So for pretty much all semester long, we've been talking about matrix equations AX equals B. And at this point, you might think that we've said everything there is to say about it, but actually we haven't. So suppose you have a matrix equation AX equals B and you want to solve it. But plot twist, what if there is no solution? Well, earlier in the semester, we would have just said, well, there's no solution, nothing more I can do for you, we're done here. But now we know that there is something you could do. You could try to find the best approximate solution. So what does it mean to find the best approximate solution? What it means is that we're trying to find x such that a times x is as close to b as possible. So the question is, how do you do this? And it's going to turn out that there is a very straightforward way to do it, but it's going to take us a little bit of work to get there. So let's think a little more carefully about what's going on in this situation. First of all, let's remember that the set of all vectors of the form a times x is the definition of the image of A. And as we know, the image of A is a subspace of Rn, where n is the number of rows of A. And then we know that if Ax equals B doesn't have any solutions, then that means that B isn't in the image of A. Now, last time we saw that if you have a point that's not on a subspace, and you want to find the closest point that's in the subspace, then you can find that by taking the orthogonal projection. And so this means that if we wanted to find the best approximate solution, we could do it by solving the problem A times x is equal to the orthogonal projection of B onto the image. Now, if A has orthogonal columns, then we could solve this fairly quickly just using the orthogonal projection formula. And that's exactly what we talked about in the last lecture. But what if A doesn't have orthogonal columns? We need to find something else that'll work then. So I think it might be helpful to draw a picture of this situation. I've got the image of A, which is a subspace, and so I'm drawing it as if it's a plane. And then I've got B, which is a vector that's not on that plane, and its orthogonal projection, which is the vector on the plane which is closest to B. But then I'm labeling that orthogonal projection as AX because that's the equation that we're trying to solve. But then I can take that third edge of the triangle and turn it into a vector, and as a vector it would be B minus AX. And then just by the way that we created B minus AX using the orthogonal projection, we know that B minus AX is orthogonal to the image of A. And so this gives us another way to interpret the problem, that we're trying to find an x such that B minus AX is orthogonal to the image of A. All right, so just to summarize where we are so far, we know that to find the best approximate solution to AX equals B, we need to find an x such that B minus AX is orthogonal to the image of A. But how do we do that? Well, one thing we know is that the image of A is spanned by the columns of A. So that means that asking that B minus AX is orthogonal to the image of A is the same thing as asking that it be orthogonal to all of the columns of A. And now it turns out that there's a nice and simple way to implement this condition using the transpose of A. So let's take a little brief detour to talk about the transpose. The transpose of a matrix is obtained just by exchanging the rows and the columns of the matrix. So for example, here's a 3 by 3 matrix and its transpose. You can see that the columns of A transpose are the rows of A and vice versa. And it's worth pointing out that you can do this even if the matrix isn't a square matrix, but then the transpose would have different dimensions from the original matrix. So then there's a simple but important observation we can make, which is that A transpose times x equals 0 if and only if x is orthogonal to the columns of A. To understand this, I think it might be helpful to look at the examples that are here and imagine multiplying A transpose times a vector x. When you do that calculation, you are exactly taking the rows of A transpose and dotting them with x. But the rows of A transpose are the columns of A. So in other words, the entries of A transpose x are dot products of columns of A with x. And so the only way that you get A transpose times x is 0 is if all of those dot products are 0, which would mean that x is orthogonal to all of the columns of A. Okay, so now that we've established that, we can go back to the original thing that we were trying to do, which is that we were trying to find the best approximate solution to AX equals B. And what we knew was that we could do that by finding an x such that B minus AX is orthogonal to all of the columns of A. But now we know that Being orthogonal to all of the columns of A means that when you multiply by A transpose, you get 0. So now we have this nice equation that A transpose times B minus AX equals 0. And now this is the equation that we want, but we can rewrite it in a way which is a little bit more straightforward to solve. So first of all, we can distribute over the parentheses, and then we can move the A transpose AX to the other side. And so then this is the equation that we want. So let's introduce a little bit of terminology. This equation, A transpose A times X is equal to A transpose B, is called the normal equation of AX equals B. And this is the equation that solves all of our problems. It's really amazing. Just by the way that we arrived at this equation, we can deduce the following facts. First of all, the normal equation is always consistent. There always exist solutions. And then second, is that the solutions to the normal equation are the best approximate solutions to the original equation, AX equals B. And so the final method that we've arrived here is so simple that if I just told you what it was without going through all this work of proving it, there was no way that you would believe me. But here's how it works. If you have an equation AX equals B that doesn't have any solutions, multiply both sides of the equation by A transpose. This will give you the normal equation. That always does have solutions, and those solutions are the best approximate solutions to AX equals B. Okay, so here's an example. Suppose we want to find the best approximate solutions to AX equals B, where A and B are given here. So probably the first thing we should do is check to see if there are exact solutions. The question seems to suggest that there aren't any exact solutions, but we should check that. And so we do that by just trying to solve the equation. So we make an augmented matrix, we put it into reduced echelon form, and when we do that, this is what you get, and you can see that the system is inconsistent. So now we'll try to find approximate solutions, and to do that, we multiply both sides of the equation by A transpose. So symbolically, this gives us the equation A transpose AX equals A transpose B. But since we have numbers for A and B, we can actually calculate the things that are on both sides of this equation. So for the left side, we would just calculate A transpose times A, and when you multiply those two matrices out, this is what you get. And then for the right side of the equation, we need to calculate A transpose times B. So when you do that, this is what you get. And so to solve the normal equation, we would make an augmented matrix out of this matrix and vector that we just calculated. And then you put it into reduced echelon form. And you'll notice that now the system is consistent, and that's not a coincidence. That always happens with the normal equation. And so then you can solve in the usual way. In this case, x3 is a free variable, and you can solve for x1 and x2 in terms of x3. And so then you can write out the solution as a vector, and what we get is the answer to the question. These are the best approximate solutions to AX equals B. And it's worth pointing out that even in this situation where we're looking for approximate solutions, the answer appears in the form particular plus homogeneous, where that homogeneous part is actually the solution to AX equals 0, so it's the homogeneous equation for A. There's a good conceptual reason why this happens, and to see it, it might help to go back and look at the picture that I drew on the first slide of this lecture. The idea is that we're looking at the orthogonal projection of B onto the image of A, and we're trying to find the x's such that A times x is that orthogonal projection. So really, we're solving an equation that's of the form A times x equals something. And really, the normal equation is just a proxy for that equation, which allows us to solve it without actually calculating the orthogonal projection. But while I think it's nice to have this conceptual understanding, it's not necessary at a practical level. All you really need to know is that to find approximate solutions, multiply both sides by A transpose, and solve. Okay, so here's another example, and this is something where we use the concept of best approximation to do something that could be useful in real situations. We talked earlier about how you can use orthogonal projections to find the formulas for best fit lines in statistics. But you're actually not limited to lines. You can do it for any finite dimensional spaces of functions, actually. So to illustrate that, I'll do an example where we find a quadratic function that best fits a set of data. So to do that, you would start just by writing out a general quadratic function. So I've got f of x is a plus bx plus cx squared. So in an ideal world, we would want the graph of this function to pass through all of these data points. Now, that might not be possible, but that's the ideal that we're aspiring towards. And so what we want to do is write down the set of equations that a, b, and c would have to satisfy for the graph of f of x to pass through each of these data points. For example, for f of x to fit the point 1, 1, then we would need a plus b plus c to be equal to 1. This comes from setting x to be 1 and also setting f of x to be 1. And then for f of x to fit the point 3, 4, we would need a plus 3b plus 9c to be 4. This comes from setting x equals 3 and f of x equals 4. And then you can do the same thing for the remaining points. And so what we end up with altogether is a system of linear equations in the variables a, b, c. And if we could solve this system of equations, then we would have a quadratic function that actually passes through all of the data points. However, as you might expect, this system doesn't have any solutions. And as usual, you can check this just by putting the augmented matrix into reduced echelon form and seeing that the system is inconsistent. And so to find the best approximation, we need to pass to the normal equation. And to do that, we need to calculate A transpose times A and A transpose times B. So here's A transpose times A, and I'll warn you that the numbers get pretty big, but luckily we have computers to do the calculations for us. And so when you multiply these two matrices together, this is what you get. And then we can similarly multiply A transpose times B. And now it's just a matter of making an augmented matrix and putting it into reduced echelon form. And when you do that, you get the solution that A is minus 267 over 280, B is 64 over 35, and C is minus 1 over 56. Who knew? And so you put those numbers back into f of x, and you get the formula for the best fitting quadratic. I encourage you to graph these data points and see how well this quadratic fits those points.